Hello again, this is Jack Jackson. In this video we're going to be looking at some properties of trigonometric functions. Now first let me remind you that this series of videos that are going over here that's going through these different classes of functions assumes that you've already studied these functions, and this is just a quick review. This one is certainly no different. We're going to be covering graphs of the basic trig functions, and we're going to be zipping through them very quickly, and in a very short amount of time we're going to cover a lot of trigonometry here. So it turns out that the following functions from trigonometry are actually continuous functions. Of the 6 basic trig functions, sine, cosine, tangent, cotangent, secant, and cosecant, sine and cosine are the ones that are continuous functions, and in fact they're defined everywhere. The inverse trig functions, arcsine, arccosine, arctangent, and arccotangent, are actually continuous functions. And the functions for trigonometry that are some of your basic functions where they're not continuous, but they're continuous where they're defined, include tangent, cotangent, secant, cosecant, arcsecant, and arccosecant. Okay, so here we go. Recall that we want to talk about trig functions. When I first introduced these in trigonometry, I introduced them in terms of trig functions of acute angle only, and we deal with right triangles. And of course, trigonometry means literally triangle measurement. And so ultimately, trigonometry has at its core looking at some triangles. But we want to go beyond that. And so what we want to do is look at rotational angles. And so the idea is here is we put an angle in standard position where we put its vertex at the origin, initial side, initial ray going along the positive part of the x-axis, and we take another ray on top of that, flick it, and let it spin. And it spins to a certain point here and it stops. And if you take this point here at 1, 0 and watch how it traces in the path that it goes, which is this pink path here, the arc length of that pink path, in other words, if we could take a tape measure and measure that arc length, that would be what we call the radian measure of that angle. If we're rotating in the positive direction, it's going like this direction, counterclockwise, that we're measuring positive. If we flick it and go the other way, so we're rotating in this direction, the clockwise direction, that rotation is measured as a negative. And notice you could have, well, let's do some measurements. If you flick it and go all the way here to the opposite direction, that's a rotation of pi radians. If you flick it and go all the way back to where you started, around once in the positive direction, that's 2 pi. So a right angle here is pi over 2 radians. But you can also have angles more than pi over more than 2 pi, more than anything. They can go on as big as you want by letting it just rotate around. So if you flick this and watch the path that my little cursor is taking, and so now we're up to pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and so forth. And by doing this, you can get any positive angle, or going the other way, you can get any negative angle, or not flick it at all, not rotate at all, and you got a 0 angle. And so this gives you any real number for an angle, and we can see it as a directed length. Now, the way we do circular trigonometric functions is we take this and we take any angle for an input, which is we're measure the radian measure of that angle, which is that arc length that we just talked about, put it in standard position, spin it around, and when it spins, the terminal ray will only touch this circle one time. It can actually be any circle that's centered at the origin, and that circle has a radius r. Then you define, you find the coordinates at that point. It'll have an x and a y coordinate, and then the r value as well for the radius of the circle. And then we'll have the radian measure, which is this arc length here, which is our value t. Or sometimes we'll use theta for that. That's our radian measure of our angle. And so we define cosine of t be the x coordinate of that terminal point, that point E right there, divided by the radius of the circle r. Sine is y over r, tangent is y over x, secant of t is r over x, cosecant of t is r over y, and cotangent of t is x over y. And those are the basic definitions. Notice that we can, if we take the unit circle, that is a circle centered at the origin of radius 1, then the r becomes 1, and these formulas with r then simplify to these formulas that you see right here. So cosine of t is then just the x-coordinate of this point right here, if it's on the unit circle, and the terminal side. Sine of t is just the y-coordinate, tangent is still y over x, secant is 1 over x, cosecant is 1 over y, and cotangent is x over y, and of course all these I should have said secant of t, cosecant of t, and so forth. You have to have an input. So notice that gives us some summaries for sines. If you're in the SIGN, sine, positive, negative, if the terminal point right here on the terminal ray where it meets the unit circle is in the first quadrant, x, y, and r are always all positive. So cosine, secant, sine, cosecant, tangent, and cotangent are all positive values. If we're in quadrant 2, we have a negative x value for the point E, which would be over here now, and a negative for the x and positive for y. So the ones that are positive y, the ones that only have y, are sine and cosecant, and they're reciprocals, by the way. And so they're positive there. The others, cosine, secant, tangent, and cotangent, are negative. If it's in the third quadrant, both x and y are both negative. And so the one that has both x and y in it, tangent and cotangent, the two negatives cancel out, and you get it's positive down this quadrant, but the other 4 are negative. When you're quadrant 4, it's the x that's positive, y that's negative. So the ones that only have x in them, the cosine and the secant, are positive. The rest of them are negative. And of course, if there's other places you could be that's not in one of the quadrants, you could be on one of the axes. When you're on this quadrant right here, notice that x is 1 and y is 0. Up here, x is 0, y is 1, and so forth. And you can use that to help figure out all trig functions. You can actually visualize all 6 trig functions, keeping in mind the signs that we have here. You can visualize their absolute values on this picture here. This one picture shows all of them. So this is the unit circle here. So radius 1, centered at the origin. We spin it around. I've got a terminal side in the second quadrant. Actually, it's 2 radians right now. And this gives you this point right here. Now, we draw this triangle right here is called our reference triangle, where we drop straight down to the x-axis at a right angle. And this is our right triangle here. The x-coordinate is the cosine of this angle, and of course the angle is this arc length from here around to here, or that amount of rotation. Okay, this angle here, the measure of that angle. So the absolute value of x is this length here from C to this point right here, K, from the origin to K. And y is this vertical distance here, this red line here. And of course the hypotenuse of that triangle is just 1 in its length. But it turns out you can actually see all of the other trig functions too. Tangent can be seen if we take a tangent line at this point to the circle, which is perpendicular to this radial segment. Then we get this line here. If you go from this point of tangency out to where it touches the x-axis, the length of that segment is the absolute value of the tangent. If you take the hypotenuse of this right triangle here, so it goes from this point along the x-axis all the way back to the origin, that total length there is the secant of the angle. And then you have a little right triangle up here. This length here, this other part of the tangent line that goes from here to where it hits the y-axis is cotangent of the angle, and this vertical distance from that point down to the origin is cosecant of theta. And as always, I refer you back to my videos for more detail about anything that I say here in this. Now, it turns out that we actually have more than one representation of the trig functions. So we basically base them on a unit circle here, rotating, and then where the terminal ray, put it in standard position first, rotate through the angle T, where the terminal ray meets the side, get the x, y, and r coordinates, use these formulas here to determine all 6 trig functions. So they're actually defined in terms of this picture. But we also have another picture, a Cartesian graph picture. So there's a relationship between these. Now this is a little bit busy picture here. So again, I refer you back to my videos for more detail on this in my trigonometry videos. Now if we look at this, we see that here's our picture that we were just looking at. So we have one picture over here on the left that's the unit circle representation. And then over here we have the Cartesian graph representation. How do these connect? Well, here the purple length or pink length here is the arc length, and that's a horizontal distance here. So over here it's an arc length or an actual angle measurement. Over here it's not really an angle measurement at all. It's an actual horizontal length, an x value. But even when we see this picture, we're thinking about this picture on the left as well, and so we're thinking of the input here as being an angle. Because it is an angle over here in the left picture, it's not really an angle in the right picture. Now, we get the x and y coordinates here. Well, one way you can find the y coordinate is just this vertical length here. I've used exactly the same scale, so distance of 1 in any direction on this picture or this one here is the same length. And so notice if I just pull that over horizontally, I get this point here, and that makes this height right here, that y value, the sine of this x value. And so that gives us, if we do this for various different points as this goes around the circle, you watch my other video, you can see this dynamically, and you can see this point moving up and down. And so what happens there is you get this red wave graph, which is the graph of y equals sine of x. Similarly, we can look over here and see the x value of this point, this yellow point, is the cosine, which is this blue distance here. So I rotate that around to make it vertical and bring it across. And this vertical distance from the yellow point here to the blue one, that is the cosine of that particular x value. As we move this point, this yellow point P around this circle, this blue point's going to go up and down tracing the blue curve here. And so the blue curve then becomes the graph of y equals cosine of x. One way you can see the tangent of x, different than the way I showed you before, is to take a vertical tangent line to the circle over here, to the unit circle, at the point 1, 0. And so we have this. And if we go out from the origin along our terminal ray and see where it meets that line, then that distance from there straight down to the x-axis is the y value of the tangent, or if it's well, you take the line between these 2 points, because if it's pointing over this way, the ray won't meet that. But if you take the line, it will come down here and meet it, and that gives you the value. Now, as we bring that value across to here, then you can see above this yellow point, that's where the graph of the tangent is. Again, we could trace that around the circle, and we see that the tangent looks like this. Notice that the tangent is undefined at certain places, and of course that makes it have discontinuities. In fact, it always has non-removable discontinuities when it has one, and they're vertical asymptotes. So when does that happen? Well, it's going to happen anytime the yellow dot is right up here, well, anywhere it's on the y-axis. Either it's right up here or right down here. So for example, pi over 2 would be when it's pointing straight up, and if it's pointing straight down, that would be, say, minus pi over 2. See the vertical asymptote, this little line right here is a vertical asymptote. So is this one right here. But then there's also one at 3 pi over 2 and so forth. Now, well, the most striking thing and the most important thing probably about all these functions with trig functions is that they are periodic, that you get the same patterns over and over again. And certainly you notice that if you circle around the circle one full time, then you're just going to repeat all the values when you circle it around again. So that makes the period of sine and cosine 2 pi. Now with tangent, it actually, you get that repeating every 2 pi, but actually it repeats more often, because it turns out that the stuff that you put in the first quadrant, when you get down to the third quadrant, we're just repeating the same thing again. So it actually has a period of pi. So if you go from negative pi over 2 to pi over 2, you get one connected piece. And then each other piece is just a horizontal shift of that. Whereas, say, with the red sine graph, if you go from 0 to 2 pi, you'll get one piece. And every other piece, they're all connected, in this case, are shifts, horizontal shifts of that one piece from 0 to 2 pi. Again, all the pieces are connected, so we have one continuous function with domain all real numbers for sine and for cosine, but the pieces are disconnected at the vertical asymptotes for tangent. Okay, now, so once again, let's make sure we got this. For a sine function, The representation, we have two representations. On the representation of the unit circle, the input is theta, and it's the measure of a central rotational angle in degree. It's the signed plus or minus sign arc length from the point 0, 1 to the terminal point on the unit circle going through the entire rotation. The representation 2, x is the input, f of x equals sine of x. It's the x-coordinate of the input on the graph, which is a directed horizontal distance. And again, in the picture, we saw those as the pink distance here, and it's the exact same pink distance bent around the circle there. That part about the input, that's the same for sine, cosine, and tangent. The output's what's different. The output over here is sine of theta, which is a y-coordinate on the terminal ray here. So the output is the y-coordinate here on the unit circle. Over here, it's also the y-coordinate of this. Of course, in general, in a Cartesian graph, the output is the f value or y value or y-coordinate of the point, which is, of course, sine of x. And that's a directed vertical distance, which is actually a vertical distance of both of these. On the other hand, on the cosine function, the same thing is true of the input. The input on the left picture, unit circle picture, is an angle, which is measured in radians. On the right, it is the horizontal distance from the y-axis. That's always the same. Now, what's different here is on the unit circle, cosine is the x value. So the x value of that yellow point, or this blue distance, is the amount of cosine. But when we bring that over here, it becomes a vertical distance, not a horizontal one. Over here, that blue distance is horizontal. Over here, it's vertical. So the output is cosine of theta, which is x, coordinate, which is x, which is the x-coordinate of the intersection of the terminal ray with the unit circle in the unit circle picture. In the Cartesian graph picture, the output is y, is cosine of x, which is the f value, y value, or y-coordinate of that, which is the vertical distance. Again, same thing here for the inputs on the tangent. Now, the output over here is tangent of theta, which is y divided by the x, which is take the point xy of the intersection and the terminal ray to get your x and y and use that formula. The y-coordinate of the intersection of the line containing the terminal ray and the vertical line x equals 1 is the output over here in this picture. You take this vertical line right here and see where the line going from the origin to the point on the ray, follow the ray, or its opposite direction. Take that line where it touches this vertical line. The y-coordinate of that is the tangent. That's also the y-coordinate over here as well. Okay, now let's very quickly go through some of the properties of the 6 basic trig functions. Y equals sine of x, or f of x equals sine of x, looking at the Cartesian graphs. Now we're going to think of these mainly as Cartesian graphs. Here you can see the graph on a square scale. So this is not distorted. Vertical and horizontal distances are consistent. The scale is not consistent so these boxes aren't squares, but that's just because I've got them marked at different places. The scale is actually consistent, and you can see several periods there. You see the repeating pattern, which is sort of one of the main features. If we look at just one period from 0 to 2 pi, this is what the sine looks like. Notice it starts at the origin, goes up to the point pi over 2, 1, then back down to pi 0, then 3 pi over 2, negative 1, and back to 2 pi 0. It's increasing, concave down, reaches a maximum, decreasing, concave down, reaches an x-axis and an inflection point at the same time, switches to concave up, still decreasing to a minimum here, and then switches to increasing, but still concave up back to here, and then it repeats the whole thing over again. Domain is all real numbers. The range is negative 1 to 1. It doesn't have any vertical asymptotes. It's actually a continuous function. The y-intercept is 0, 0, so cosine of 0, 0. The x-intercepts are actually at multiples of pi, 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, negative 1 pi, negative 2 pi, and so forth. You can see that. So those are the x-intercepts are n pi comma 0, n is an integer. In other words, sine of x equals 0 if and only if x is in the set n times pi, where n is an integer. The period is 2 pi, so that says if you take sine of x plus any integer multiple of 2 pi, you get the same as the sine of the function you started with. This is sort of a horizontal symmetry, your translational symmetry. Okay, so you're translating it and it stays the same. The inflection points happen exactly where it touches the x-axis, so again those are multiples of pi, same as the roots, and it has maximum and minimum, infinitely many. And if you notice, it's pi over 2 is one of them, and then any shift of that by 2 pi. So pi over 2 plus 2n pi is the x-coordinate, and then of course the y-coordinate is 1 for all those. All those maxima are both local and global maxima. So sine of x equals 1 if and only if x is equal to pi over 2 plus 2n pi. The minima happen when sine of x equals negative 1, which is x is an element of the set negative pi over 2 plus 2n pi, where n is an integer. And so the minima have coordinates negative pi over 2 plus 2n pi, comma negative 1, n is an integer. This is an odd function. Odd function, one of the things that you can see geometrically is it has rotational symmetry about the origin. If you rotate this, the part in the third quadrant goes right back to the part in the first quadrant goes to the third goes to the first, and so forth. And so if you rotate about the origin 180 degrees or pi radians rotation, you get the same graph again. And algebraically, you see that as sine of the opposite of x is the opposite of sine x. Normally, you can't bring a negative outside of the parentheses in a function, but you can if it's an odd function, and sine is. So sine of pi plus x turns out to be the opposite of sine of x. Okay. Another thing that we can look at, cosine. Cosine is very similar. In fact, it's really just a horizontal shift of sine. We'll see that in a second. And so we have a similar kind of graph, but notice it starts at the maximum and then goes down. So if we look at one period, the same period from 0 to 2 pi, you see it starting up at 0, 1. Then it goes down to, decreases concave down to an inflection point where it meets its x-axis at pi over 2, comma 0. Then decreases concave up until it gets down to pi negative 1, increases concave up, so that's a global minimum. Then it increases concave up to 3 pi over 2, 0, which is also an inflection point, and then it increases some more concave down now until it maxes out at 2 pi 1, and then it repeats the whole thing. The next interval of 2 pi, say from 2 pi to 4 pi. So the domain again is all real numbers. The range is negative 1 to 1. It's a continuous function defined everywhere, so there are no vertical asymptotes or horizontal asymptotes. The y-intercept is 0, 1, so cosine of 0 is 1. The roots, the x-intercepts, actually are odd multiples of pi over 2. So it's pi over 2 plus 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth, negative 1 pi over 2. So it's just one way to make an odd number is this. You start with any integer, you multiply by 2, you get an even integer, add 1, then it's an odd integer. So the roots, which are also the same as the inflection points, are an odd number, 2n plus 1 times pi over 2, comma 0, where n is an integer. The period is 2 pi, and then you can see here where the maxima and minima are. Keep going on here. Next function is tangent of x. So these are sort of our three most basic trig functions. Notice this one is not continuous. So sine and cosine were continuous functions. This one's not continuous. It is continuous everywhere it's defined, but it has vertical asymptotes. Well, anytime tangent is y over x. So anytime x is 0, which are odd multiples of pi over 2, the same time cosine is 0, or when this is going to have vertical asymptote. Notice that one period now goes, for example, from minus pi over 2 to pi over 2 is one connected piece with asymptotes at both ends here. Vertical asymptotes. So the domain here is not everything. So you have to take away those odd multiples of pi over 2. So it's all numbers, all real numbers except where cosine is 0, or where x is 0 back on the unit circle picture, and these are the ones we have to eliminate. Now the range actually is all real numbers. If you look, any one piece goes from minus infinity to positive infinity. The vertical asymptotes are going to happen everywhere it's undefined. So x equals 2n plus 1 times pi over 2, where n is an integer, makes the equation of a vertical line, which is a tangent line, not a tangent line, but an asymptote. The y-intercept, the one and only, is the origin. And x-intercepts happen at multiples of pi. So it happens up here at 0 and at pi and 2 pi and 3 pi and 4 pi, 5 pi, negative 1 pi, negative 2 pi, and so forth. Tangent is an odd function. Tangent, the opposite of x, is the opposite of tangent x. And you see a few other facts there about tangent. Now, we also have reciprocal relationships. So cosecant of x is the reciprocal of sine x, and you can see that kind of in this picture. The blue graph is our sine wave, our sine function, and the other function is our cosecant function. Notice that when sine is 1 or negative 1, cosecant will be the same as sine, and they touch each other. But whereas, for example, this point at pi over 2, 1 is a maximum, a global and local maximum of sine, it's a local minimum of cosecant. And vice versa, for example, here at 3 pi over 2, comma negative 1, or negative pi over 2, comma negative 1, that is a local minimum and global minimum of the sine function, but a local maximum, not global, but local maximum there of the cosecant. Notice that the range of sine is between negative 1 and 1 inclusive, and that's except for the negative 1 and 1, that's the part that's not included in the cosecant. So cosecant, the range is negative infinity to negative 1, close bracket, union, close bracket, 1 to infinity. Similarly, you have a relationship between secant and cosine. Secant of x is 1 over cosine x, and you can see similar relationship there. Now, tangent and cotangent are reciprocals, but it's and this picture does bear that out, but it's a little harder to see, I guess. So when tangent is 0, cotangent is actually undefined, and then so everywhere tangent is 0, there's here and here and here, you have a vertical asymptote for the other one. Everywhere cotangent is 0 is where tangent has a vertical asymptote. Okay? When tangent is less than 1, cotangent is bigger than 1. When tangent is bigger than 1, cotangent is less than 1. So notice tangent increases, cotangent decreases. In fact, tangent on any one piece, tangent always increases, left to right, on any one piece. Now, not necessarily, it certainly can go down from, say, here on this piece to down here on the next piece. If you stay within one connected piece, then tangent increases all the time, and which means it would have positive slopes. Okay. On the other hand, cotangent always decreases. You can see that there. So here's some properties of cosecant. Very, very quickly go through this. You can see that there's one period there. Zoomed in a little closer. Real numbers except for n times pi are the domain, so y equals n times pi are the vertical asymptotes, or x equals n times pi are the vertical asymptotes. Already said what the range is. There it is. The period is 2 pi. And notice it's when y is positive, it's concave up, and when y is negative, it's concave down. It has a maximum on the negative part and a minimum on the positive part, local. Secant is the reciprocal cosine. You see it again there. Here's one period. Even within one period, it's two disconnected pieces. The asymptotes here happen when the function is undefined, and that happens at odd multiples of pi over 2. So the domain is all real numbers except for odd multiples of pi over 2. That is, all real numbers except parentheses 2 times n plus 1, close parentheses, times pi over 2, where n is an integer. That funky looking z there just means the set of integers. Remember, the integers are 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, etc. It does have a y-intercept here, 0, 1, but doesn't have any x-intercepts. Period is 2 pi. It doesn't have any inflection points. On one piece, it's either all concave up or all concave down. But it does have some maxima or minima. Cotangent is decreasing where it's defined. It's periodic. You can see it here. It's the reciprocal of tangent. And graphed on one period, here's what it looks like. Notice it decreases concave up, hits the axis at the inflection point, and then decreases concave down, going toward the asymptotes. And the vertical asymptotes happen at integer multiples of pi, so the domain is all reals except for in pi. The range is actually all reals. Okay, so so we have that, and we have the period is pi. Inflection points happen where it hits the x-axis. Those are odd multiples of pi. And notice there are no maxima or minima at all, because on each piece it's decreasing the entire way. Okay, continuing on, here is a couple of periods, or four for tangent, cotangent, and 2 periods for the others. And these are all using the same window from -2 pi to 2 pi and from -4 to 4 for x and y respectively. This is not necessarily a square scale here, possibly. Probably not. Okay, but anyway, here's sine, cosine, cosecant, secant, tangent, and cotangent. So just a quick side-by-side of all 6 of the basic ones. Now there's some other relationships that are interesting among the basic graphs, is that sine and cosine are just horizontal shifts. Now remember, in general, if you replace x by x plus or minus a number, you're just shifting the graph horizontally. So notice that cosine, if you'll shift it to the left by pi over 2, you'll end up with sine. And so you can see that, of course, you shift to the left by, shift sine to the left to get cosine by pi over 2. So you shift to the left by replacing x by x plus pi over 2. So if you take sine of x plus pi over 2, that becomes cosine of x. And similarly, if you flip it around backwards, take cosine, shift it to the right by pi over 2 here, you get sine. And so that gives us our horizontal shifts between those two basic functions. So the way you affect a shift to the right is you replace x by x plus something. So this is x plus a negative, actually. X minus a positive will go to the right. So replace x in cosine x by x minus pi over 2. That's going to shift to the right by pi over 2, and you'll get sine of x. Now, because that's the case, then you also get the same amount of horizontal shift here on the other graphs here. So if you shift, let's see, this one is cosecant, and if you shift it to the left by pi over 2, you get secant. So that gives you the second equation. And here you can see the shift going to the right the other direction. Now tangent and cotangent are not shifts of each other. Look at this. One's increasing, the other's decreasing. So even though they have a reciprocal relationship, they're not shifts. Okay. Okay, so that gives you a quick overview of the 6 basic trig functions and some of their basic properties. And we'll come back and look at a few more classes of functions here at the next couple of videos.